Okay, let's continue on, stress intensity factor. The second topic I want to talk to you about is a relation between energy release rate G and the stress intensity factor K. Okay, so far what we did, first major topic that we talk about is energy release rate, and we see how that control the crack behavior through the energy release rate, which is, the energy needed to advance the crack by the unit area. And we see another parameter that is stress intensity factor. Okay, now think about these two as complementary approaches because the energy release rate is a global analysis. We are looking at the energy, accounting for all the energies associated when the crack advances. We take into account the work done, the increase or decrease in strain energy inside the material as the crack advances, and that formulates a threshold criterion based on G. Now, stress intensity factor is a local parameter, right? Because this describes the stresses and displacements around the crack tip. Okay, this is a local analysis that allows us to look at, so to speak, more details around the crack tip. And both of them are equally true, right? So we're evoking two different principles. This is, balance of energy, conservation of energy principle, and the stress intensity factor is an application of the Newton's second law, which is just the equilibrium of or the stresses and the deformation of the material around the crack tip. So both of them have, they are both very commonly used. In fact, because they are actually describing the same physical behavior, there is a relation between them, and we're going to, quickly look at that and establish that relation. Now, this relation is more complex if we deal with other materials with plasticity or nonlinear materials. But in linear elastic materials, there's a very simple relation between these two, and I can show you this relation. You can obviously you can already derive it yourself too. So I'm calling it this the GK relation. It's a classical relation, also due to the work of Irwin. Now, so I'm going to show you a quick example just to show you the relation, and I'm going to go through a derivation, which I believe is is important to be aware of. Now, before we go to derivation, we can deduce this relation very quickly from the simple example of the Griffith crack. Again. Look at this Griffith crack problem, right? Again, the same problem we've been looking all along, right? So this is the one that we have very simple solutions, and we can formulate very simple results. So the stress intensity factor K, that's what we just arrived at today. K1. This is a mole1 fracture, so it's equal to sigma squared root pi a. Now, energy release rate for the same problem, which we derived maybe 2 weeks ago, that is pi sigma square 8 over E. All right. And if you look enough, carefully enough, all the parameters are pretty much shared. They appear both in the K1 and also the G expression. And so a very simple looking for the common variables will allow you to, come to this expression, right? So, for example, if you just take K1 and just take the square of that, you're going to get sigma square pi a, and that's exactly what you see in G divided by E. Now, so just collecting that is very straightforward to look at the GK relation. Now, this is energy release rate is related to Ki square K1 square over E. Now this has two forms because the G, the expression for G here is based on a derivation of a plane stress assumption, right? So when we derive this, this is assumed to be a thin plate, And you know, there's also the assumption that was used in Griffith, you know, and that expression corresponds to a plane stress result. Now, if you have a much deeper block, then you are getting into the situation of plane strain. And in that case, your energy release rate is going to change. It's not just going to be this, but instead it's going to be dependent on also the Poisson's ratio, right? Just because that there is some stress in the thickness direction, and that will contribute also to the strain energy. So I'm not going to go through that. But I'm just going to show you the end result. The plane stress we're showing here just by taking these two together, and you get this one. Now the plane strain is very similar, but then you have a term that depends on the Poisson's ratio in front of it. So it's 1 minus nu square. Okay, so this is just the GK relation, but now we have not actually proved it. This is the you know, the true in general, right? Because we just equate those, and this is only for Griffith crack, right? These relations. So it may not work, you know, by just, you know, this is not enough evidence to say that this relation is true all the time, right? We know it is true for Griffith crack by just me looking at these results. But we can actually do that proof fairly easily. That was the first done by Irwin. Okay, now so what I'm going to sketch out the analysis. It was simple enough that you'll be able to understand and also, you know, to reproduce. So this is the crack closure analysis by Irwin. Okay, so the way to think about this is that we want to understand G relation between G and K, and K relates to the stress field, right? So we kind of have what K is. We know what K is. I mean, it has to be related to the crack tip stress field. Now G is the energy, right? So you know, and G is, you know, the difference in the potential energy, which is the difference in the strain energy, and the strain energy comes from the stress field. So what we need to do is just to relate, you know, the corresponding, you know, stress field expressed in terms of the stress intensity factor K, and equate that to the G, right? So how do we do this? So to do that, you know, we need to think about two configurations, because, you know, a crack extension analysis or you know, crack growth is we're always comparing two configurations. So I hope by now you understand the process. You know, this is the same process we followed when we were looking at the energy release rate. So there's a crack. So we're going to do this analysis kind of in reverse. So usually we start with a crack with shorter length, and then it extends. Now Irwin did it in the other way. So he was looking at two configurations. So this is the crack width that has a longer crack length. This is the crack with the shorter crack length. So think about, all right, so you have a crack here, and it starts, it will propagate at some point and become this configuration. Okay, so what we want to do is to compare the change in the potential energy, which then defines the energy release rate. Now, if you recall, the energy release rate is potential energy versus the crack length. All right. So now, so I'm gonna go quicker. So I'm not gonna go through every single step, but then I'll just remind you of the basic definitions. Potential energy of the system, we have the work done, and we have the strain energy inside the material, right? So we want a difference between these two as the crack length goes, right? So we are looking at a change in the potential energy, and that then boils down to getting the change of du, the strain energy between these two configurations, and the change in the work done. Now, the change in work done is zero because we assume it to be. That's because we have the in this problem we pose we would have the crack, sorry, the plate that is gripped by two plates, and the plate don't move in between these two configurations. So the plate, the grip on top and bottom, they are not moving, and therefore there is no displacement of the applied force, and therefore there is no work done. So we went through this analysis before, so I'm not going to go in detail. So what we're looking at is basically this expression, right? So we want G, and we need to find out delta U versus delta A. Now so just to be vigorous, we're looking at as A goes to 0. Okay. So we need to account for delta U. Okay, and so just writing that down, we have delta U, and so the delta U is the change in strain energy. So if we compare these two configurations, the change in strain energy, it is only the change in the part of this region where the crack has grown by by delta A. Okay, so the rest of the plate, they're going to have the same stress, right? Because this is an infinite plate. So we have a crack that goes by extend by delta A. Then other areas will have the same stress level, far away from the crack, and far behind the crack, right? So those areas, the stress field don't change because what is only changing is the stress around the crack tip. Therefore, the difference is going to be 0. So we don't have to account for that. So the only thing that has changed between these two configurations is this crack has extended, and therefore there is energy that goes into previously we have stresses that in front of the crack, and now since it's extended, this region is no longer taking the stresses that it should be taking, right? So that's the only change in the stress field, and the change of the strain energy then is the amount of the stresses that is applied in this region multiplied by the corresponding the strain, the strain deformation of this region. Now, and that is actually equal to the amount of displacement that the crack has opened, right? So originally there is a crack here, so the two pieces of material, they're intact, but this point has moved up to here, and likewise along this whole line of delta A, they correspondingly moved up because the crack has gone through. So this is the displacement, and that displacement was acted on by the stress. So that is basically the the sort of the work done by that internal stresses, right? And that actually is the work, the strain energy difference. So what we need to do is to multiply that stresses in front of the crack tip in this configuration, and we already know how much displacement it has gone at this point. Okay, so we just have to multiply the force with the displacement. And that is the only region that changed, because right now, if you look at this configuration, all the stresses are now the same here, right? Then the same as in front of the crack tip. The crack tip stress field is universal, right? It's always the same. And so what we need to do is just to calculate that energy by this region, coming out from this region. So now if we're going to write this down, is energy change. So we just write du, the strain energy corresponding to this region of the body, and and this goes from x equals 0. So I'm putting the origin here just for easier calculation. So x0 to delta A. Okay. So and then the rest of it is going to be the same. There's not going to be any change in the no more difference in the string energy. Now then what we need to do is to write the U. So how does the string energy varies as a function of x? It varies as a function of x. The string energy and density, that's because the stress field and the displacement are varying with coordinate x. Okay. So I'm going to write this down by writing down. So we have the force, that is the force that creates that is present in front of the crack when it is closed. So we have let's call that Fy because it's in the y direction. It's a function of x because we need to write down the energy, which is a force times displacement. And that is the work done. Okay, and what we need then is to look at the to turn that into stresses, right? This is Fy, right, which is the the work done. Basically, the string energy is the area under this curve. Okay, and we know what the stress is, right? So we just need to turn that into corresponding stress. Because we know this crack tip stress field, which is then the sigma yy times uy, and we both also know that the displacement uy expression. Okay, now we just need to go back and find out these terms, right, from the universal crack tip stress field and substitute the corresponding values, right? So let's do the displacement first. We have uy, and if we go back to the displacement of a mode 1 crack and look at the theta equals 0, right? So because we're looking at the crack in front of the line in front of the crack, you just pick out that solution. What you're going to get is the following, right? So this is kappa, which is a constant depending on the elastic constant. And we have K1, which is the stress intensity factor, right? Because the displacement is written for stress intensity factor over 2 nu. Now 2 nu is the shear modulus. Okay, so you will see this expression in the expression in the displacement. Okay, and what we need is then you will see this is r over 2 pi. Now r is the amount this displacement from here to here. So r goes from delta A to minus x over 2 pi. Okay, this is uy. Now what we need is the sigma x, sigma yy, right? Now sigma yy is simple because again sigma yy in front of the crack, that is just when theta is 0, that it has a very simple expression which is given by K1 2 pi 2 pi x, right? So r is x in this in this coordinate system. So what we need to do is then put all this together, these two expressions, into here, and then we integrate. So that's all we need to do. So let me clear out some space here so we can do that integration, but leave out this. The same equations here, and so I have the the full derivation also on the lecture notes, so you don't have to copy this, and you don't have to look at this handwriting either. So what we need is putting these together into this, and then we integrate. So I'm going to write down the final form. We want limit delta a as goes to 0, kappa plus 1, and then you'll find that you have 2k1 square and 4 pi mu delta a. So just look at this, because we have here 2 pi is being taken out. Everything that is not dependent on x, we taken out. So the only thing that is dependent on x, on the sigma y, is the square root x. That's why you see it here. The only term that depends on x from u is delta a minus x. So I put it right here. Everything else you just take it out, right? So you have ki squared kappa plus 1, and then you have the 2 as there as well. So it gets to this form, and we can keep going. And then if we do that integration, this is again fairly simple integration and some simplifications. You get to a form that is this. And now what you need to do is to look at what kappa is. Now kappa can be depending on plane stress or plane strain, they are different. So I'm writing this down for plane stress, right? Because kappa, we talked about this in the first part of the lecture. Then they are related to the Poisson's ratio, so they can be related to this. So this is a more general derivation because it does not assume anything on the external boundary conditions. All the analysis we've done is locally around the crack tip. So this is a crack closure analysis. So in the end of the day, you get a the expression that we just obtained from looking at the G and the Ki for Griffith crack. Okay, so this is again a very simple relation, which is also quite remarkable because sometimes it's easier to calculate G, sometimes it's easier to calculate K, and so if you know one, then you know the other. So for example, we can do the double cantilever beam, which we already find out G, right? And instead of solving the stress, finding out what Ki is, the stress field around the crack tip, what is the Ki around the crack tip of the double cantilever beam, you don't have to, because that is quite difficult to find Ki. Finding out the stresses, solving the boundary value problem, and finding out all the stresses is fairly difficult for DCB. But then we can find out the energy release rate from DC beam, and depending on whether this is a thin beam or a very thick beam, that either you're in plane stress or plane strain, then you can find out what is the corresponding Ki, right? The stress intensity factor for DCB, right? Sometimes it's easier to find Ki, so I'm going to show you some solutions that later on, show you some solutions on Ki that we've computed and people have studied before, and we can vice versa calculate energy release rate, right? So in the literature, most people use the stress intensity factor. You see that more, the kind of the K approach more than G. So I don't know why both of them are equally good. They're the same sort of looking at the same, reviewing the same physics from different two different perspectives. Okay, so just one final summary slide for all this. Now this is what we did is for mode 1. The derivation is also for mode 1. So similarly, you can do that for mode 2 and mode 3. So it's also not difficult to do. You just need to repeat the crack closure analysis, but now assuming this is a mode 2 fracture, and then you have the stresses and the corresponding displacement. So you're not looking at Uy anymore. You should be looking at Ux, because that is the in mode 2 you have displacement along x direction if you apply a shear force. But then in the end of the day, the sort of expressions you get is the same, basically. And for mode 1 and mode 2, just by switching the K1 with K2. In mode 3 is also basically the same, just that you have K3 here, and then on the bottom is the shear modulus nu. Okay, so this is the GK relation. So bear in mind that we use GK relation quite a lot, to go back and forth, so this presents a very convenient way to analyze fracture problems. So because sometimes we can measure fracture energy easier, because fracture energy is is dependent on the sort of surface energy if you have a brittle material. So you might want to get fracture energy without doing a fracture experiment. So that's one thing you can do, and then you can convert it to the stress intensity factor. So then it allows you to then study a crack problem. All right. So this is all for today. I'm going to continue on stress intensity factor. We're going to define another parameter which is called the fracture toughness, and then we're going to formulate a second criterion, fracture criterion based on K. Okay. I'll see you 2 weeks. In 2 weeks.